All right, the complement of set A, and it's written as an A with a line on top. It's kind of like the opposite of. These are the set of all elements that are not in A. Okay, so we define it symbolically as this complement of A is any element of the universal and any element that is not in A itself. Okay, so that's how we define that something is the complement of set A. Okay, we define set B to be a subset of set A, and we write it as B is, it's not quite a less than, let me be very clear about that. It looks like a sideways U. If and only if every element of B is an element of A. Okay, so let me get more clear on this. So we're saying that B is a subset of A means that every element of B is an element of A. Okay, that does not mean A is a proper subset of B. Now, if that is true, so if, this is another statement then, if B is a subset of A and A is a subset of B. Okay, so what that means, so B is a subset of A means everything in B is in A. If I also tell you that everything in A is in B, I can also then conclude, knowing that A and B are the same set, right? Subset simply says that there's stuff in B that I know is in A, and if I say that everything that's in B I know is in A, and everything that's in A I know is in B, then that means that they have to be the same set. Okay, we can go a little bit more in detail, and that's where this proper subset is. So let me kind of draw this out here. So here's our universal set. Here is set B, and I'm going to tell you that B is a subset of A. So A has got a bigger bubble than B does. So what that means then is there's got to be something in A that's not in B. In which case, we simply say that B is a proper subset of A. They're not equivalent to each other. At least I don't know they're equivalent. Well, I know actually in this case I know they're not equivalent, because I know there's extra things in A that B doesn't have. Okay, the last thing we want to address in this section is this idea of subsets in a finite set. So let me start by just defining a couple of sets. So let's say I've got set A, and I'm going to put one element in there. How many subsets live in set A? Okay, well, one subset is the empty set, so the set of nothing, and then one subset is the set of everything. Okay, so the kernelity of set A is 1, but there are 2 subsets. All right, let me broaden our perspective here. Let's go with set B. Set B is going to have 2 elements, A and B. Okay, how many subsets exist in with a set that has 2 elements? Well, we have the empty set. We have the set of A. We got a set of B, and we have a set of both, A and B. Remember, if I go BA, it's the same as AB. Order doesn't matter. So there were 4 subsets. So the cardinality of set B was 2, and yet we were able to produce 4 subsets. All right, what do you think's going on here? All right, doesn't it kind of look like there's some sort of factor of 2 going on? 2 to some power, I guess, times 2 maybe. Let's do our little experiment on to 3 subsets, or 3 elements, sorry. All right, so if C's got 3 elements, how many subsets can we come up with? Well, we have the empty set, we have the solos with single elements, we have the doubles, so we got A and B, we got B and C, and we have A and C, our 2 element sets, and then we have the triple, A, B, and C. So how many subsets was that? Let's see, 1, 2, 3, 4, 5, 6, 7, 8. Okay, so 8 subsets, and it's got a cardinality of 3. Okay, so let's look at our numerical pattern here. Doesn't quite, I mean, it looked like we were doubling there for just a second, but now that we looked at 3, we've got 8. So it's not that we're doubling, but there is a factor of 2 involved. Okay, so in general, there are n elements in a set. That means there are 2 to the n subsets. So it's 2 to that power. So for example, if there were 4 elements, that means I would be able to generate 2 to the 4th subsets. 2 to the 4th would be 16. So it'd be 16 subsets. So anyways.